right, so welcome back, and welcome to this second modulus of this sort of, say, fundamental overview of some tools, which are actually instrumental for what we are going to see this afternoon and let's say, in the last 2 days of the course. So before starting, I will ask questions like Miguel, but I would say I will go much on the easy way. How many of you know how to calculate a spectrogram? Raise your hands. It's not valid, just say, I type spectrogram in MATLAB. Huh? Okay, so quite some people.
Can we use Google?
You can use Google, okay? If it takes more than 5 minutes, then maybe it's better to listen here. And how many of you already surf on wavelets? Okay, there are some users. All right, if you raise the hand twice, then you can sleep tight for the next hour. Well, hopefully you will not snore too loud. Otherwise, let's take this trip, and I will try to be more operative. So say, I will open MATLAB, so in case you have MATLAB, you can open it, at least the first code, I'll try to type it so that you can follow and try to get the same results on your screen. So let's say the starting point is the Fourier transform. We saw it already with Miguel. You have, say, the continuous transform, then the discrete form. Actually, so this is a Fourier series, and that's basically what you're doing is changing the base. So you take your signal, you transform it into a different base, which is a whole bunch of sines and cosines with different frequencies, so say harmonically related. And interpretation as just a change of base is quite trivial. If you look especially for the discrete form, you have a signal that is discrete, is made of n samples. You transform it into some other n numbers that are complex, okay, and are the coefficients of this expansion. Well, I'm not going to be exhaustive, of course, but there are examples of applications that are huge and that say are all over the place. Just to give you a few of them that might be more interesting for us, one that made it very popular for fluid mechanics is transforming the PDEs in ODEs. This is the basic example, or you take the 1D heat equation, and you see that, say, you take an equation is a partial derivative, so you apply the Fourier transform in space, so imagine you have an infinitely long bar, and then you obtain that since, say, in the Fourier space, the derivative is just a multiplication of the frequency, then you obtain an ordinary differential equation, which is much easier to handle. Filtering data, I guess you're all familiar. You take data that have some noise, like this blue curve, you apply a filter, and then if you have a nice separation between, say, the frequencies of your data and what the noise is, which is typically wide in most of the experimental application, then you can obtain a beautiful filtering of your data. Or compression, you take an image, then you pass it to the Fourier domain, and then, say, in most cases, images are smooth, say, they have long features, long regions where features are actually not varying much, like in this image, and so you can actually chop the reconstruction, you just retain the strongest coefficients, and you'll end up with an image which is actually beautifully resembling the original one, in this case with just 0.5% of the coefficients. This was actually quite an easy image to filter. So in the end, say, this is practically the cornerstone of a lot of engineering applications. So ranging from communication, every time you make a phone call, you're actually passing through something that uses the Fourier transform in some way, okay? So some elaborated form of Fourier transform to compress your data and make the transfer easier, as well as in computational physics, in CFD, use spectral methods to solve the Navier-Stokes, and advanced data analysis. And the key feature, let's say, what really made the big change is the FFT algorithm. So you have a very efficient algorithm which scales very well with large amount of data. You know that this operation here involves n squared operations. If you use the algorithm by Cooley and Turkey, introduced in 1965, you actually need n times the logarithm of n, which scales much more gently with the number of samples. And then, let's say, for continuous stuff, say sinusoids is actually quite a gentle basis where you can decompose your signal. So like in the image, for example, you have, say, smooth features, you can easily reconstruct it using sums of, say, continuous sinusoids. The problem starts when you have stuff that has information, frequency content that is varying along the signal. And the problem is that if you look at the formulation, in both cases, you're actually using, to determine your FT expansion, you're actually using the entire sequence. So let's say here you see you have a time integration, and here, for each coefficient, you're actually using all samples of the sequence, which means that you're giving up the time information to get something that is in different domain, that is that of the frequency. There are, of course, several cases where frequency changes over time, and it's interesting to look at that. One example is, for instance, if you think of music, and actually, let me go. This is a spectrogram representation of a piano concert of Beethoven, and what you see here is, in the vertical direction, we're actually going to do it, is the power spectral density of the music that is playing. So you see that the frequency content is actually changing over time, and it might be important in some cases to localize the feature where they're actually occurring. Or just another trivial example is heartbeats. So these are the data. This is actually a built-in example of MATLAB. These are data from the Kobe Heartbeat of 1995. And you see here that if you look at this sequence, there's actually, say, quite a long time where this is practically noise. There's very little activity there. And then you see that there is one spot where you start having, for like 3-4 minutes, more or less, some activity, then there is another period is quiet, and then you have another spot with large fluctuations. Whoops. That was Heartbeat. Let's see. I made the system crash. That's awesome. It's rehearsing. Let's see. This just restarted. I don't know why. Let's see it again. Sì. Something happened here. I don't know what's going on. Sì. No. Aspetta. Sì. Yeah. Sì. Due secondi riparte, rapido. There you go. Okay. So too much shaking, maybe. Let's get back to this. So apart from earthquakes, of course, you can easily imagine that you might be interested to know where some event with a certain scale is occurring. Finance, for example, in the stock market, you want to know when a certain stock item is experiencing some resistance or some support or is making some fluctuations. In biology, for example, the electrocardiogram is a beautiful example where you want to filter out information. You know that what you're measuring is actually voltage differences outside of the body, so they're very weak, and the electrocardiogram is contaminated, for instance, by the 60 hertz of the light that is incoming. So you want to filter out, but at the same time, you also want to retain information about arrhythmias, for example. Okay, so you don't want to get a full sequence, say, okay, your heartbeat is whatever, 100 pulses per minute. You want to know whether there are various variations over time. And of course, if you think about turbulence, we know that it is multi-scale, but actually it's very interesting to see whether you can catch, if a certain scale that is active, where it is occurring. I mean, the spectrum is interesting, but it's even more interesting knowing where the actual scale is located. So how do you handle that? Well, if you think for a moment to the electrocardiogram, to the earthquake, what is the workaround, the easy one? Well, what you can do is to take this signal and you split it. Okay, so if you want to localize, just make it shorter in time. It's a very simple workaround, and then for all these sequences, you calculate the corresponding spectrum, and you identify that in that second window, for example, you start seeing some peak there, okay, so say around 50 millihertz. And then say you have in the last one, you have two peaks, which are two different activities. Of course, here you pay a price. The price is that the shorter the sequence, the less is your frequency resolution. So you have troubles in looking at the stuff that is occurring at, say, the large wavelengths, the low frequency of the spectrum. So this is the price to pay. And apart from that, such a, let's say, such a trick actually has an even larger price, that is that of basically what you're doing is windowing your signal with the boxcar function, which is as long as the window you're selecting, and then actually you know that it introduces ripples in your spectrum. So you might want to do something more gentle, and that is at the basis of the Gabor transform. So what you do is practically, let's say, change your kernel of the Fourier function with a window. This window is sliding all over the signal, okay? And say one of the popular kinds of windows that you can use, and this is actually the one introduced by Gabor, is a Gaussian function. So what you're doing is replacing your sinusoids, which were going all over the domain forever and ever, you're actually replacing with Gaussians that are modulated. So they look like waves that are actually reaching a maximum and then decreasing with the Gaussian. So, for example, imagine that you have a signal like this one. It's a signal where you have two well-localized frequencies. You have two sinusoids, and you want to know locally the frequency content. Then what you can do is to pre-multiply the signal by this window. You make it slide, so you make shifting along the whole signal, and then locally what you get out, and this is actually not, let's say, an accidental choice, what you get out is that the sinusoid actually, let's say the function forming this expansion will actually look like this. They look like waves that are sort of smoothing to create a time localization of your spectrum. And then you can keep going. You can move the window all over the signal. And what you can do is to create a representation where you take all the spectra, you pile them up as columns, and say for each time, you put all one close to the other, and you get something similar to what we saw with the Beethoven piano concert. So say, for instance, these two would be something like this. Okay? So in order to do that, we can try to do it in MATLAB. So if you have MATLAB now, you can open it, and you can try to follow what I do. So basically, first operation, we clean the environment. I don't know, you don't see it. Whew. That's annoying. That's annoying because I have to code over there. It's duplicated now. Well, okay, so we can use actually right away the code here. Okay. So first of all, what we do is to generate the signal. I'm taking a sequence that is, say, 2 pi of length with 2,000 samples. Okay. I generate my spaced samples, and I select two frequencies. One is 3 hertz, the other one is 10 hertz. And then there is a parameter that I have to select that I partly overlooked before when describing the Gabor transform, is the standard deviation. Yes? Is zoom it in? Okay. Actually, what we can do is to go here. These are in the folder anyway, okay? Better now? Perfect. Okay, great. So what I actually overlooked before is the standard deviation. Evidently, when you make your windowing, you need to select how big is your window. So whether it is a sharp one or it is a large one. So here I've set like something like 0.5, which is the same that you find on the slides. And then what I do, well, first of all, I generate the signal. Okay, so it's just the sum of the two sinusoids, and putting here this Boolean here is just say switching on and off a sinusoid in a certain domain. And then I calculate the spectrum, so we can actually stop here, see first the spectrum. There you go. Okay, there you go. You also have it on. You also have it on the slides. Okay, so we can clearly see from the full spectrum, we actually identify the 3 hertz We actually identify the 10 hertz without problems, but we don't know where they are, right? As we saw before with Miguel. So we want to know now where they are. So what I'll do is to make the window slide. Okay. So actually what you see here on top, this one is the window that I'm sliding. Below you see the signal that is pre-multiplied, and here you see the spectrum. And you see how it widens up. Okay, then we start seeing the second peak here as the window is arriving at this point. We see a lot of ripples, okay, around. That's because this sinusoid finished quite sharply. And then as the last step, we can actually see how the spectrogram looks like. Okay, so here we have a frequency representation. We actually identify quite well that in the range from 1 to 3, we have a frequency of 3 hertz. This is a logarithmic scale. And then at 10 hertz, this is in the range 4 to 5, which is what the sinusoid was actually showing. And now what I'll show you is what happens if I change the window. So if I make it sharper or if I make it wider. So what I'll do now actually is to remove the close all so that we can update and see what goes on, okay? And take a sharper window, for instance, 0.2. Okay, so you see now our window is much sharper. You actually start seeing where the problem might start. We don't see enough cycles of this sinusoid now. So this is making us suspect, and indeed we see it here, that we don't have enough frequency resolution to see it fine. That's because our window is very sharp. Nonetheless, on the other side, this actually were very well localized, just because of its sharpness. Indeed, if we go ahead, you see now, this is the new spectrogram, and now we see that the definition of the interval is much better, right? Just because our window is much better localized for both cases. What happens now is that this peak is sort of broader, right, with respect to what we saw before. And we can actually look at that. We can compare the two of them. There you go. This is the other one. You see here the peaks are much better defined. So we see that there is a sort of compromise in between the time definition, the time resolution we have, and the frequency. We cannot have both. Either you use a window that is very well localized, and that will tell you in a nice way, which is a time resolution. So that large part of the wavelet goes outside of the domain. So say, normally when you make analysis like this, you should do the same also for the spectrogram, by the way. You cannot really rely on that part, okay? Let's see how we go with the time. Ah, perfect. So any questions so far on this first part? Yes?
A question and a comment from Stefano Discetti. When you apply continuous wavelet transform to white noise, you can also see beautiful features appearing.
Yes, that's true. That's true. That's true. What we can typically see when we use white noise is that the coefficients tend to decay. Sorry, not tend to decay. They tend to spread quite uniformly, but you see some decay around. Okay. So actually, yes, you can see patches, and then say extracting single scales sometimes is hard to do it. Okay. In this case, I think it was quite evident, and indeed, I didn't risk to say anything about what's going on there because actually it's very difficult to tell. There are the patches around here, they're quite well defined and they seem consistent. So I think that they're something that can be safely said. Yes.
I see a very nice lecture. I see that you are using wavelets, cosine, and so on. And there's a good reason to use it because these are the least biased ways of filter for general data. Now you can imagine that you have some data where you have essentially only sawtooth behavior. So it quickly goes up and then it slowly goes down. And for this type of data, one may envision another way of encoding the data. Say, just putting a scale and the location of these things. Do you see a way how one can derive, say, more suitable filters for a given data? So this refers to the question which Xavier has asked at some point. No, this is a coding problem or complexity problem of finding something like a good language which compresses the information out of your data. And of course, if you are data specific, there may be other filters which may encode your information much more effectively.
Okay. So the word of wavelet, it's very varied. Okay, and actually that is where the human input enters. I mean, depending on your kind of application, you can find or design following some simple guideline the wavelet that you like the most. Probably in the case you're referring, it would be better to search into some data-driven choice, so not imposing it. Okay, and that's just to avoid what you're saying. That otherwise you put a bias. Okay, so probably it would be better. It will be better to search for something that auto-encodes directly what your data are saying.
So it's a common theme. So when we are talking about physics-based encoder, you can also make a physics-based analysis. So at the moment, you know that your data comes from a certain system of ordinary differential equation and so on. You can already include this knowledge in your physics.
It's a sort of supervised way of seeing the problem. Yes, I agree.
I have a last question. Maybe you mentioned it, but I missed it. Which kind of wavelet, which shape of wavelet did you choose, and how to choose the proper wavelet? Like Mexican hat, all the dB, 1, 2, 3, 4, whatever.
Okay, for this we will need much more lectures. Okay? But this one, I just used the default one of Madrid is the Morse wavelet. Okay, it's the Morse wavelet. Okay. In principle, it depends very much on what you want to do. Typically, wavelets are used, for instance, especially discrete one, for compression of images. And the nice thing is that they preserve edges. Okay, so typically when you blur an image because you want to get rid of the noise, you don't want to blur the edges because it's, let's say you feel much less comfortable, you prefer having noise rather than blurring the edges. In that case, the R wavelet that is sharp is actually doing quite a good job. If you want something that is more continuous, okay, so if you're looking at something that has some continuity, doesn't have spots, like this might be the case, then you go towards like the Morad wavelet, for example, or the Mexican hat. And then I said before, example, if you know that you're searching for Gaussians, that is the case when you have particle images, then you go to the Mexican hat, you don't have doubts. So it really depends on what you're looking at. And then, as Bernd was saying, for some problems, you might want to search into, say, data-driven choices. That's another option. I think it's a beautiful field where you can investigate. Okay. Any other questions thus far? Yes?
So for the low machine wavelets, you mentioned that it has vanishing moments.
Yes?
But can you remind what are the properties and interests? I mean, why would you want to have vanishing moments for a wavelet?
And the nice thing of vanishing moments is that it makes it easier to represent smooth stuff, basically, if you want to make it in a very simple way. Okay, so that is what makes those functions interesting. And typically, most applications, when you search for something that's not that aggressive, it requires some smoothness, then looking at functions which have this kind of properties might be useful.